Simple harmonic motion, or SHM, describes the back-and-forth movement seen in objects like swings or springs. When an object moves around its equilibrium position in a regular, repeating way, that's SHM at work.
Simple harmonic motion is a type of periodic motion where the restoring force is directly proportional to the displacement and always points toward the equilibrium position. In practical terms, the more you pull an object from its center, the stronger the force pulling it back. For example, in a mass spring system, this relationship is described by the formula F equals -k times x. Here, F is the restoring force, k is the spring constant, and x is the displacement from equilibrium.
Several key features define SHM. First, the restoring force always acts to bring the object back to the equilibrium position. Second, acceleration is greatest at the extremes of motion and zero at the center. Third, velocity is fastest at the center and zero at the endpoints. Finally, SHM has a period, which is the time for one full cycle, and a frequency, which is the number of cycles per second. These features help us analyze and predict the behavior of oscillating systems.
For SHM, formulas are essential. In a mass spring system, the restoring force is F equals -k times x, and the period is t equals 2 pi times the square root of m over k. For a simple pendulum, the period formula is t equals 2 pi times the square root of L over g. These equations allow us to calculate how long each oscillation takes, making it easier to analyze real-world systems. For example, if a spring has a mass of 0.5 kilograms and a spring constant of 200 newtons per meter, the period is about 0.314 seconds.
In simple harmonic motion, displacement, velocity, and acceleration are out of phase with each other. Displacement and acceleration are 180 degrees apart, meaning when displacement is at its maximum, acceleration is at its minimum in the opposite direction. Velocity, on the other hand, is 90 degrees out of phase with displacement. Understanding these phase relationships helps explain the timing and movement of oscillating objects.
Simple harmonic motion is fundamental to understanding many systems in physics, from swings to springs and pendulums. By exploring its features, formulas, and phase relationships, you gain a solid foundation for analyzing oscillating motion. These concepts are essential tools for solving real-world problems in physics.